Chapter 7 is all about energy. So energy is the ability to do work or produce heat. Work is force acting over a distance. So if you push a desk, you are doing work on that desk. If your friend comes by you in the hallway and bumps into you and pushes you into the locker, that friend is doing work on you. So it's a force applied that causes something to move, basically. Heat is a flow of energy due to temperature difference. That's what we're going to focus most of this chapter on, is heat. Potential energy is stored energy. And in molecules, that energy is stored in the bonds. So taking methane, for example, methane is the gas that we use in the lab. So this is the structural model of methane. It's carbon in the center, and it's single bonded to 4 hydrogens. And in each of those bonds, energy is stored. And when you break those bonds, you release that energy. In the lab, we see that when we spark the Bunsen burners and the gas ignites, and that energy is being released, in that case, in the form of heat and light. Kinetic energy is energy of motion, movement. The formula for kinetic energy is down there. Ke is 1/2 mv squared, m being mass, v being velocity. So you won't have to use anything with that formula in this class. Just be aware that kinetic energy is related to mass and velocity. So in this picture, ball A has potential energy. That guy's holding it at the top of the hill. He's going to release that ball. It's going to roll down that hill. It's going to hit ball B. When it hits ball B, what's going to happen is ball B is going to move. But if this, let's say this was 5 kilometers. Oh, that's a really big distance. But anyway, let's say it's 5 kilometers. B is not going to move 5 kilometers. Some of that energy from A is going to be lost. So it's going to depend on the surface. If A is rolling over a rough surface, it's going to lose a lot of energy to heat. And so it's not going to be able to push ball B very far, which means it's not going to be able to do very much work on B. How much ball A pushes ball B is how much work it's doing on it. So if it's losing a lot of energy over this rough surface to heat, it's not going to be able to do very much work on B. It's not going to be able to push it very far. Whereas if it was a smooth surface, it would be able to do more work on B because it would lose less energy to heat. So it would push B farther. But notice here, work and heat will change depending on the surface. But the change in energy is the same regardless of the surface. Ball A at the top of that hill has a certain amount of energy. How that energy is transferred, though, whether it's as work or heat or both, depends on the surface. The law of conservation of energy states energy cannot be created or destroyed, only transferred. It can be converted from one form to another. So like with the methane example, that was chemical potential energy that then was converted into light energy and heat energy. So energy cannot be created or destroyed. It can be transferred. It can be converted from one form to another. A state function is a property of system that does not depend on the pathway. So if I'm traveling from Chicago to Denver and I take the northern route, it's 1,050 miles. If I take the southern route, it's 1,245 miles. This is not a state function because depending on the pathway, I have a different value. I have a different amount of miles that I am traveling. So that is not a state function. If I'm looking at elevation, however, going from Chicago to Denver, Chicago is 580 feet above sea level. Denver is 5,280 feet above sea level. So horizontally, traveling from Chicago to Denver, the route is going to matter, right? Depending on if I go the northern route or the southern route, there's going to be a different amount of miles that I travel. However, vertically, I'm traveling up 4,700 feet, regardless of if I'm taking that northern route or that southern route. So yes, this is a state function because it's the same value no matter the pathway. I'm going up 4,700 feet no matter how I get there. So are these state functions, energy, work, and heat? We'll start at the bottom. Heat is not a state function. As you remember from the picture, the amount of heat transferred is going to change depending on if we have a rough surface or a smooth surface. So that's not a state function. Work is not a state function because the amount of work that ball A was able to do on ball B changed depending on if it was a rough surface or a smooth surface. But energy is a state function. The amount of potential energy that ball A had was the same regardless of the surface. And so it did transfer all of that energy. It just transferred it in different ways depending on the surface. So energy is a state function because the change in energy is the same. Ball A gets down to the bottom of that hill, it releases all its energy. And that amount is the same regardless of if it's a rough surface or a smooth surface. Temperature is a measure of the average kinetic energy of the particles of a substance. Temperature and heat are not the same thing. Heat is energy that is transferred from warm objects to cold objects. Temperature is a measure of kinetic energy of the particles of a substance. So in the left side here, this has high energy. We can tell that because the lines are big. So it's at a high temperature. On the right side here, this is a lower energy because it's at a lower temperature. So I just mentioned heat. Two systems with different temperatures that are in thermal contact will exchange energy. Thermal contact is really just contact, period, at all. You're in thermal contact with the air, you're in thermal contact with whatever you're sitting on, anything you're touching mostly. The quantity of thermal energy transferred from one system to another is called heat. So if you come in and you sit on a cold chair, you are going to transfer energy to that chair. And that energy that you transfer to that chair is called heat. So heat is a flow of energy between two objects due to a temperature difference. Heat always flows from warm to cold until they are the same temperature. The symbol for heat is a lowercase q. So I have hot water and cold water. The hot water is at 90 degrees and the cold water is at 10. So the hot water is going to transfer energy to the cold water. That energy is called heat because it's energy being transferred due to a difference in temperature. So that hot water is going to transfer energy to the cold water until they reach equilibrium, until they are both 50 degrees Celsius. The universe can be divided into two parts, the system and the surroundings. The system is the part of the universe on which you are focusing your attention. It's where the action is happening. So if salt is dissolving in water, the system is salt because it's dissolving. If water is boiling, the system is water because it's boiling. So it's whatever's doing the action. That's your system. In chemistry, the system is oftentimes the reactants and products in a chemical reaction. The surroundings is everything else in the entire universe. Energy being absorbed or released is always indicated from the system's point of view. In an exothermic process, energy is released by the system. In an endothermic process, energy is absorbed by the system. So you can see there, exothermic, the system is releasing energy to the surroundings. Endothermic, the system is absorbing energy from the surroundings. Those two quantities are equal. So the energy absorbed by the surroundings always exactly equals the energy lost by the system. So this match has potential energy, and its match head, it has chemicals, and in those bonds is chemical potential energy. When I strike that match, it's going to release that energy, and it's going to release that energy into the surroundings. And the exact same amount of energy that that match released is the amount of energy that is put into this, is absorbed by the surroundings, because the energy absorbed by the surroundings exactly equals the energy lost by the system. Thermodynamics is the study of energy. The first law of thermodynamics is the law of conservation of energy, which we've already covered. Energy cannot be created or destroyed, or another way to say that is the energy of the universe is constant. So energy is transferred from one form to another, but the amount of energy, the total amount of energy in the universe, is constant. Internal energy is the sum of kinetic and potential energies of all particles in the system. This can be changed by the flow of work or heat or both. So your first formula for this chapter is delta E equals Q plus W. Putting that into English, triangle delta means change in. So the change in energy of the system is going to be heat plus work. I'm going to skip this slide for just a second and go here because this is important to being able to answer the question on the other side. So thermodynamic quantities always consist of two parts. A number giving you the magnitude of the change. Is it 2 joules that are transferred or is it 2,000? And then a sign indicating the direction of energy flow. This again is always from the system's point of view. So if you have an exothermic process, the system is losing energy. The total energy of the system goes down. And so you show that with a negative value. You cannot have negative energy just like you can't have negative mass, but we show that energy is being released by having a negative value. In an endothermic process, it's a positive value. The system is absorbing energy, so the total energy of the system goes up. So Q would be positive. So now going back to this question, a system releases 125 kilojoules of heat. Heat is Q. 104 kilojoules of work is done on it. We are going to calculate delta E. So delta E is Q plus W. Delta E is my unknown. Q is 125, but it is releasing 125 kilojoules of heat, and so we're going to show that as a negative 125 because that's being released. And then W, 104 kilojoules of work is being done on the system. So because the work is being done on the system's absorbing it. So that's positive. So delta E is negative 125 plus 104. Just put the units in. So delta E is negative 21 kilojoules.